Hey, just got the green light. Well, we're about to start our seminar today, and I'm obligated to let folks know that they should be aware of the exit signs in case we need to leave the room on short notice. And having said that, the folks that are in the watching on the internet, we encourage folks to send in their email questions at first opportunity, so if we have enough time on the air to take them and not disappoint anyone. So with that, John?
Thank you, Peter. Well, thanks everyone for coming today. I'd like to introduce our speaker, Mr. Greg Pannone. I need my glasses to do that. Greg Pannone is president of CT Energy, LLC, a Michigan-based analytics and software company focusing on energy efficiency for the transportation sector. Previously, Mr. Pannone was head of fuel economy, performance, and powertrain synthesis at Chrysler Group, LLC, where he was responsible for the strategic planning and technical development activities necessary to achieve Chrysler Group's competitive and regulatory fuel economy and CO2 requirements. Prior to that, excuse me, sorry about that. Prior to that, he spent nearly 25 years in engine and powertrain systems development at Chrysler. He led the powertrain systems development of many engines, including the Hemi V8. Before joining Chrysler, he was with General Motors Powertrain for 8 years at the Warren, Michigan Technical Center. Mr. Pannone holds a bachelor's degree and a master's degree in mechanical engineering from the Missouri University of Science and Technology and a master's of applied statistics from Oakland University. He has authored and co-authored technical papers on alternative fuels, engine technology and control, exhaust emission, aftertreatment, and fuel efficiency. He's here with us today to describe his work modeling the fuel economy benefits that could be achieved in the light-duty fleet if all vehicles in the fleet adopted currently available best-in-class load reduction technologies. This work will help ARB assess the path forward toward achieving the ambitious goals of the Advanced Clean Cars program. And during the presentation, as Peter said, you can submit questions by email. They'll be answered at the end of the presentation, and same with the audience. If we could, hold questions until the end. And with that, Greg.
All right, good afternoon. Over on this side. Again, thanks, John, for the introduction. Technical analysis of advanced clean cars. Just a couple of first, a disclaimer. This work is CONTROLTEC statements, don't represent those of California Air Resources Board. Also, if we mention anything on commercial use of software or anything, it's not implicit that it's an endorsement of these products. From an acknowledgement standpoint, this is a fulfillment of contract 13-313. I would also like to acknowledge my technical partner here, Heidi Schroeder, who did an immense amount of work on this program. It's about 1,400 vehicles that have to be analyzed, had to be analyzed for this program, so a significant amount of detail went into that. Also appreciate the feedback we got in the many conference calls we had with the Air Resources Board and their partners at the EPA, and that's some good conversation there, some good feedback. So what I'm going to cover here is motivation, objective, and scope, just to make sure we're all aligned. A vehicle load primer, for those of you who don't work in this area a lot, just kind of level sets everybody on vehicle load and what we're going to talk about. Then the assessment of the model year 2014 vehicles from an aerodynamic drag, tire rolling resistance, and mass. Vehicle load reduction scenarios that we then ran based on that information, and the fuel economy and CO2 projection results that came out of that. We'll make some conclusions, and then at that point we'll open it up to Q&A. So we'll start with the motivation and objectives. As John said, this is part of the Advanced Clean Cars program, and I think also midterm review, to support the midterm review. And so the question really came back from the Air Resources Board is, what potential does vehicle load have in reducing CO2 emissions? And very specifically, the research task was that if every manufacturer could move every car to best in class, what would be the potential of reducing the fleet? So specifically moving aerodynamic drag, tire rolling resistance, and mass to best in class. So as a former OEM person, I would say this is a very large competitive assessment to start out with, where you're looking at every car in the fleet and seeing how far you can move each. Just want to touch on the scope, because this comes up a lot, what the scope is and is not. It is focused on 2014 model year light-duty vehicles to set the baseline. It is about aerodynamic drag, tire rolling resistance, and mass. We're focused on the EPA combined cycle, so that's 55 city, 45 highway, and it's an analytical study. What it is not is we're not getting into powertrain technology with this research. We're not looking at alternate drive cycles, NEDC, which is the European, JCO8, Japanese, and WLTP, for instance. We did not do any testing here. We evaluated test data, but did not actually do any tests, and it does not include a cost assessment. So we're going to start out with a vehicle load primer, just to, again, level set individuals on what we're talking about. When we look at vehicle load, or when we look at CO2 emissions, we look at it from an organizational viewpoint, where there's an organization that handles vehicle load, and there's an organization for energy conversion efficiency. Under the vehicle load elements, you have what we call road load, mass, and then drive cycles as part of that. Under road load, aerodynamic drag, tire rolling resistance, brake and hub drag. And under mass, it's the weight of the vehicle plus inertia. And of course, drive cycles play an important part on the importance of vehicle load. On the energy conversion efficiency side, that's really the powertrain elements, as most would call it, the powertrain elements. We're not going to talk about those today. We're going to talk about the items highlighted in green and orange. This organization chart happens to be a way a lot of manufacturers also organize. You have vehicle energy folks that worry about aerodynamics, tires and aero, and you have the powertrain folks that worry about the energy conversion efficiency. Drive cycles are defined by folks like some of you in the room, regulatory agencies, consumer, and of course nature, and that is a very important aspect of vehicle load. Just to frame vehicle load and its importance, this chart shows all 1,300 vehicles, 2014 on the EPA cycle, fuel consumed as a function of tractive energy. So the best measure of vehicle load is tractive energy. And tractive energy is that combination of aero, mass, tire. And you can see in this example about, and this is true for every model year, about 70% of the variation in fuel consumption among all the vehicles that are sold new is due to vehicle load, variations in vehicle load. So along the x-axis, here is tractive energy. And I pointed out a couple cars here. This first car is a Mitsubishi Mirage, very small car if you're familiar with it, 3-cylinder engine. And then I'm going to go to the other end of the spectrum and look at a Lincoln Navigator. Very large vehicle, has a different function, handles more people, tows. But what you see there is, if we look at the fuel consumption units there and compare the two vehicles, there's about a 3 times difference in fuel consumption. You go from about 1.5, in this case I'm looking at energy per mile, and I'm going up to about 4.5. So it's about 3 times the fuel energy. The tractive energy on the x-axis here is also about 3 times. So the tractive energy of the Lincoln Navigator is about 3 times the tractive energy of a Mitsubishi Mirage, and its fuel usage is about 3 times greater. What else does that mean? We're not going to talk about efficiency elements today, but that also means the efficiency of those two powertrains is about the same, and that surprises a lot of people. How can an efficiency of a 3-cylinder engine be the same as the efficiency of a V8? Because those two powertrains are matched to the vehicle, so they can achieve the similar efficiencies. Now, in this organization that we're talking with, we care about CO2. So CO2 is a simple conversion when we're talking about gasoline, not talking about electric here for this example. When we're talking about gasoline, it's a simple conversion of that y-axis on the previous chart. And now I'm putting it into grams per kilometer CO2. Same trend here. The Mitsubishi Mirage is about 110 grams per kilometer in this example. The Lincoln Navigator is up around 320. 3 times the tractive load, 3 times the CO2 for the same efficiency. Some may ask is, what about the scatter here? Vertically, the scatter is due to efficiency. Okay, so the difference between a car down here being very efficient and a car up here being inefficient, and that difference in CO2 is due to the efficiency of the energy conversion elements. So we're looking specifically on this research, what is the impact of tractive energy or vehicle load on CO2 emissions? Now the importance, as I said earlier, drive cycle is important in terms of its, the vehicle load impact and the elements themselves. So people say, how important is aerodynamics, or how important is mass, or how important is tire? It depends on how the car is driven. What I'm showing here is some of the primary drive cycles globally. I have the EPA city and the highway, the first two, the EPA combined, the next, and then the USO6, the SCO3, which is the air conditioning and aggressive cycle, then the current European cycles, and then just a 65 mile an hour cruise. So the gray bars represent the effect of specifically mass and kinetic energy. What percentage of that tractive energy is going to overcome that? The blue is the percentage to overcome aerodynamic drag, and the green is the percentage to overcome tire rolling resistance. The orange and red are the hub and the brake drag. They're small, certainly important elements, but small elements. So you can see, depending upon the cycle, the significant difference in what's important. Is it mass, is it aero, is it tire? So there's not one single answer of which is most important. If you're cruising down to San Francisco and you're driving 65 miles an hour, then you care about aerodynamic drag. If you're on the NEDC urban cycle, it's a much more mass-intensive cycle, more accelerations that put in. One thing to note, and we'll talk about it a little later, is that the green bar, although that's tire, mass is also a factor there, because as I put more mass on the tire, the rolling resistance goes up. So there's actually 2 elements to the green bar. There's an element of mass in there, and then there's the element of rolling resistance. We're going to be focused on everything we're going to talk about today. We're going to be focused on the EPA combined cycles. So how important are these for what we're talking about today? We've analyzed lots of cars, done lots of analysis in the past, and the numbers we use across a wide range of vehicles would be a 10%, this is for the EPA combined cycle, a 10% reduction in mass would be a 5.6 reduction in tractive energy. 10% aerodynamic drag would be a 3.6% reduction in tractive energy. And a 10% reduction in tire rolling resistance would be a 2.1%. So the point of this is you do not get a one-for-one impact on tractive energy. Meaning if I reduce my mass by 10%, I'm not going to get 10% better fuel economy. I'm going to get 5.6% or less, depending upon powertrain matching. And again, as I said earlier, mass impacts both tire rolling resistance and overcoming kinetic energy. So let's walk through the assessment of the model year 2014 vehicles. So again, the question from the ARB team was, what if everybody moves to the best in class? What's going to be the impact on CO2 and fuel consumption? So the first thing we have to do is figure out where everybody is. So the task goals here is, in this particular task, non-mass, is find out what levels of aerodynamic drag and tire rolling resistance every model year vehicle and every variant in the fleet, which we counted up 1,358 variants. So what is a variant? And this is very important to understand as we go forward. A variant is a body style powertrain combination. So if we think about a pickup truck, which is the most complex variance, most pickup trucks will have 3 cab sizes and 3 bed sizes, and most will have a 2-wheel drive and a 4-wheel drive, and most will have 1 or 2 or more engines in them. So if I use an example of, say, a Chevrolet Silverado, by our count, Chevrolet Silverado is 52 variants. Okay, so we needed to understand the aerodynamic drag and tire rolling resistance of all those. If you think about another car, a Ford Fiesta, it's a sedan and a hatchback. It's a different variant. So often if you go into the EPA database and look at the labels, there's less variance than 1358 because labels are done collectively. So pickup trucks have a single label for a powertrain. Once we figured out the aerodynamic drag and tire rolling resistance of every vehicle, we needed to identify top performers and then define best in class, because best in class can have a broad definition. And then also cross-reference these to the vehicle features that were on, the features were on these vehicles. So this is a part of the research project that we're not going to spend a lot of time on today other than voiceovers, but we did a literature review ahead of all of this analysis to see what was on the fleet and tried to correlate that back to top performers. So for aerodynamic drag, the best measure of what we're talking about here is the coefficient of drag, or C sub D, and it was reported by about 47% of the manufacturers. So of the 1,358 variants, we had about 700 reported CD variants. And quite frankly, of those 700, some of them were the same value for a range of vehicles within that. So there might be a pickup truck that, as I said, had multiple body styles, but there was one aerodynamic drag number. We knew that that's not technically correct. But even if every manufacturer reported 100% of aerodynamic drag, test standards are not the same from wind tunnel to wind tunnel. Most aerodynamic drag numbers are measured in a static wind tunnel. Those will vary. There's enough technical papers out there to indicate that. So we did not want to use, so we had 2 problems here. We knew there's variation in the measurement, and we did not have measurements for every vehicle. So challenge number 1 for this research was find a consistent method to estimate the coefficient of drag for all the vehicles in the data set. Next came tire rolling resistance, and RRC, or the rolling resistance coefficient, which is a common value used in industry, is, we felt, the best comparison in this case. Tire rolling resistance as a numeric value is not reported by the manufacturers, nor could we find much information in literature from the tire manufacturers themselves. So very little information on tire that we could find to support this. There are some government funded programs from a few years back. We'll go through that. But our challenge number 2 here was to find a consistent method of measuring tire rolling resistance, or estimating tire rolling resistance for each of the vehicles in the data set. So how did we do that? Our approach was to decompose the road load. So again, we're on the non-mass area. So the road load is, the y-axis here is the road load force. I'm just showing it in newtons. The units don't really matter. And the x-axis is the vehicle speed. And of course, as vehicle speed goes up, road load goes up. So more force required to push that car through the air as we go up in speed. That curve is generated by a set of coefficients that we call in the industry ABC coefficients. Those are required by the certification process on every model variant. So when exhaust emissions are tested or fuel economy is tested, these road load coefficients are required. So we had those available for every model variant in the fleet. So we knew we could use those. Then we had to decompose it. So this is the same plot now, decomposed to the elements that form that road load. So in the blue is aerodynamic drag. In the green is tire, so those are the 2 big ones that we're looking at for this study. The orange and red are the hub and brake drag, and then the gray at the very bottom is a consequence of how this is tested. It's just the driveline drag. So we have analytic methods that we can decompose every vehicle this way and come up with measures of aerodynamic drag and tire rolling resistance. Now, one of the key importance here, and we talked a little bit about it earlier, you see that as you go across the speed range, the percent importance of that element changes dramatically. So at a low speed, say 30 kilometers per hour, it's mostly about tires. You go up to a highway speed at 110 kilometers per hour, it's mostly about aerodynamic drag. So we took this method, Heidi decomposed 1,358 vehicles down, and now we'll walk through the results of these. So this chart is the result of all 1,358 vehicles broken down and aligned by vehicle type or body style. So across the x-axis here, I have the different body styles that we looked at. So coupe, convertible coupe, sedan, hatchback, wagon, SUV, van, and pickup. And then across the y-axis here is the coefficient of drag, the CD. Now, several trends pop out that made us comfortable with these results. Number one was you see the variation in CD, average CD across the bottom here. Those follow what we would expect in terms of the trends that we would see. Pickup trucks generally have the highest CD because short cabs, open beds create a lot of turbulence. Sedans tend to be the best, very good shape, especially. But you do see and SUVs have the widest variation here because you have a very wide design space in the SUV. So at the bottom you have the sleeker SUVs, and the SUVs up here at the top are the ones you may expect. I'm not going to name names, but they're boxy. You can know what they are. So things followed trends. Over here on the coupe and the convertible, you see those ones sticking out. Those tend to be the performance vehicles. Performance vehicles, if they don't use an active device, need something to pull the car down to the road at high speed to avoid lift. Those are often detrimental to the coefficient of drag. So as we went through this and vetted out this information, it all followed well. I don't show it here, but it is in the report. We did correlate it against the 47% of vehicles that reported. I should say this method measures what we would call the dynamic CD. So most vehicles, when they're measured for drag in a wind tunnel, it's a static, meaning the tires are not turning and the road is not moving. There are wind tunnels in the world that have moving roads and spinning tires, but most do not. So what we're analyzing here, because we're decomposing it from a road load, which is theoretically from a coast down, which has moving road and rotating tires, we'll have a higher CD on average, and that's what we saw. We saw a CD of about 15 counts, 0.15 counts higher on average than the manufacturer's values, but there was a significant amount of spread in the manufacturer data versus our data. Again, we believe that it's partly due to wind tunnel reporting, differences among the manufacturers, and we also had to estimate frontal area to get CD. It's in the report on how we did that for all 1,358 vehicles. So to satisfy this research, we had to select best-in-class aerodynamics. So we knew, and you can see it from that previous slide, that aerodynamic drag is variable by body style. So minimally, we had to have a classification that recognized that. We didn't want to come to the end of the research and say that a pickup truck has to have the same aerodynamic drag as a sedan, because we knew that's not plausible or logical. So we did want to classify these to identify best in class. We looked at sample sizes, we looked at a lot of data, we looked at distributions, and we came up with 8 different body style classifications to define to put each vehicle in that class and then define the best in that class. So we looked at distributions across each of those and made our evaluations and proposals and presented those to their resource board team, vetted back and forth a bit, and we came up with really in recognition of the body style variance, measurement and analysis variability that's just inherent in this, we define best in class as the 90th percentile. So what I'm showing here is a distribution of the three classes of vehicles with the largest number of vehicles in them. That's sedans, SUVs, and pickup trucks. And here I'm just showing the distribution of those three classes, aerodynamic drag versus the frequency of the vehicles in that class, so standard distribution and you see here in the sedan is 0.274 is the 90th percentile. You see the average sedan is around 0.3 today by our measure. SUVs varied, as I said earlier, the widest variation from just around 3.3 CD all the way up to near 0.55. The 90th percentile there being 0.322 by our measure. And the pickup trucks more narrow because they're more common with each other, about 0.385 is best in class by our measure. So 90th percentile is the definition of best in class. So going back to what we were going to talk about earlier, we're moving everybody eventually, once we get down to this scenario, move all these cars that are not best in class to best in class. So these vehicles out here would move down to that level. Vehicles that are better than best in class for the final load scenario, we left them there. They were already best in class or better. We did not want to, and that's the team, the ARB team and ourselves, not task a best in class vehicle with getting even better. Just bring the industry up. So these are the final results by our analysis of the 8 classifications. So coupe convertible, sedan, hatch and wagon. We lumped hatch and wagon together for a couple of reasons. When we looked at the data and the distributions, there wasn't a significant separation in aerodynamic drag for hatch and wagon. And the wagon segment is pretty small. There's, I think, less than 20 vehicles in the wagon segment. So we lumped those together. SUVs, and then the only other separation here was the minivan and the full-size van. So that was a special case. The full-size van, currently the vans that are in the full-size van class today are all just say the older design vans for 2014. But there's a transition coming in the industry to, I'll say, the more aerodynamic full-size vans that are out there. So in that particular case, we looked at using the 2015 certification data, we looked at what the new vans were doing. So as an example of that, Ford has an E-Series van that you know today. You drive it when you go to the airport and they take you to your parking space. That is eventually going to be phased out with their Transit, which they introduced, I think, this year. So the Transit has better aerodynamics. So we looked at these newer vans to understand, and we set then the best in class evaluation at the new van level, 358. Pickup trucks, we looked at different cab bed combinations, but when you start to separate the vehicles down to individual cab beds, the sample size gets far too small to break that out. Overall, what we're seeing here from aerodynamic drag standpoint is relative to the median, which I'm showing there in the middle column, we're looking at an 8 to 14% reduction if median today to best in class today, 8 to 14%, depending upon the class of vehicle. So remember that number when we get down to the load scenarios. So let's go to tire rolling resistance next. I'm going to jump right to the result. This is the distribution of tire rolling resistance that we found after looking at the 1,358 vehicles. We have tire RRC. The units there are kilograms per 1,000 kilogram, or if you're in the English, it's just the same pound force per 1,000 pound force. And we're seeing anywhere from about low 6s, high 5s out to about 16 RRC. Now, unlike aerodynamics, we did not have a baseline to compare to because aerodynamics, the CD is reported by manufacturers, so at least we had a reference point. In the case of tires, we had no reference point because it is not reported in the literature. We did go back to look at what our distribution looks like to a study of original equipment tires. We had to go back to 2009. So as part of some studies, the Rubber Manufacturer Association put together a series of, it's about 400 to 500 tires, original equipment tires, and that was, their distribution is plotted in green against our distribution in blue. So there are differences. We are close from an average. So our average that we found in the 2014 fleet is 9 kilograms per 1,000 kilograms. The RMA data was at 9.2 kilograms per 1,000 kilograms. There are some differences in the distribution there. We are estimating more activity down in the 7 and 8 RRC range, and more activity out in the high RRC range. Although the median of the two distributions is very close. Why would we expect to see that? A couple things. That data from RMA is 6 years old now, 7 perhaps. We don't know what has happened with tire rolling resistance in that time. The vehicles, the RMA data may have been off new tires rather than run-in tires, which is part of the coast down procedure. And the tire size, wheel size, tire width of the RMA data was much narrower than the 2014. So a lot more tire variety in the blue set versus the green set there. But by comparing it against the RMA data, we at least got some comfort that our analysis methodology was consistent with what has been measured in the past. So again, as with aerodynamic drag, we needed to understand best in class. But just like with aerodynamic drag, we know that tires have other things they have to do. They have to have, we have to be cognizant of wear, braking, wet traction, noise, other things. So we evaluated, based on some vehicle classifications, different categorization of tires. We came down to 3 categorizations of tires. And again, as with the aerodynamic drag, we looked across the distributions to understand what the distribution of our RC was and then how we could set the best in class. So this happens to be the distribution of all the tires now broken out into the 3 classes that we ended up with. A fuel economy class, a balanced class, and a performance class. We did look at off-road class. The sample size was small and it looked very similar to balance. So let me explain each of these classes. So if a vehicle was specifically a fuel economy oriented vehicle, or it was the fuel economy oriented model within a vehicle, it got binned into the fuel economy class. And that doesn't have to only be small sedans, Toyota Priuses. Their Silverado XFE, it's a fuel economy version of that truck, can go into that class. So, or if the manufacturer specifically said in their write-up that it was a fuel economy tire on the vehicle, we put it into that class. For the performance class, it was really, if it was a performance-oriented car, and we classified those tires, or those vehicles, into tire classification of performance. Those are all the vehicles that we would expect. So the performance cars from Europe, the performance versions of cars, or SRT for Chrysler, Corvette for GM, those kinds of cars that we would all agree are performance cars, got binned into the red. Okay? So the separation and and the balance then is everything else. And why did we call it balanced? We just said we would expect in those cases the manufacturer is trying to balance that tire across the needs of rolling resistance, wet traction, braking, wear, noise, and not necessarily trying to optimize either end of that, just trying to find a balance for their vehicle. The majority of the vehicles fell into the balanced category. But the separation of these distributions is what we would expect again. Fuel economy vehicles have lower RRC, the performance vehicles have higher RRC. Now, recognizing there's variation there, we also didn't have any information on rolling resistance for 2014. We backed off on the percentile, also recognizing that tires have to do more than have low rolling resistance. We used the 75th percentile here to define best in class. What does that look like in the end? These are the three categories that we put each car in for tires. Sample size for each, so you can clearly see that the balanced category is the majority. The median RRC for 2014, and then our best-in-class evaluation point. So as with aerodynamics, when we get to the end, if we had the car in the fuel economy class, its tires would get moved to 7.4. If it was already at a 6, its tires are not going to get moved. So we're moving all the tires that are above 7.4 in the fuel economy class to that value. Balance 7.7, performance 8.9. Overall, compared to the median, we're 11 to 14% lower rolling resistance if a median tire versus a best, what we're defining as best in class. So that's aerodynamics and tire rolling resistance. Now we have to get into mass. Mass is difficult. So the task from the ARB team was to generate a metric for mass, to quantify mass efficiency. And then once we quantified that, determine the mass efficiency of the 1,358 vehicles, identify the top vehicles, just like we did with aero and tire, and then, again, define that best in class. Because we're not always saying, as with tire and aero, the best in class is the absolute lowest value. It's a logical value that we believe is plausible and probability achievable. And then cross-reference that with vehicle features. The last point was part of the literature review, and relative to the literature review, there's some manufacturers report a lot of information on the mass and mass usage. Other manufacturers don't report anything. So that part was certainly somewhat difficult. So the original desire was to look at the subsystems of the vehicle, body in white, powertrain, and try to do some kind of substitution analysis where we pull off of all steel body in white and put on aluminum, or take off a steel door and put on an aluminum door. There was not enough consistent information out there to do that. So we had to come up with another method. Given that lack of information, we already had a mass efficiency model or mass model developed that we had done for some of our other work, so we leveraged that mass model. So let's talk about that mass model a little bit. It's a light-duty mass model that we've assembled over the last 4 years or so. We use it to identify vehicles that have good mass efficiency or vehicles that have opportunity for mass reduction. We use publicly available information, because if you've got to populate this and check out a vehicle, and there's 1,300 of them, you have to really rely on the public information from the manufacturer. The model is a combination of continuous and discrete elements, and it's assembled like the car itself. So there's the base vehicle portion that takes into account the length, width, height, cargo bed, wheel size. There's the powertrain portion that takes into account what type of engine it is, spark ignition, compression ignition, is it turbo, non-turbo, supercharged? If it's a hybrid, what kind of hybrid is it? What's the size of the motor if it's a hybrid? Also then the next discrete element is the transmission and driveline. What's the transmission type? What driveline? What's the driveline architecture? And then finally the onboard energy storage element, which is fuel capacity, fuel type, battery capacity, and battery chemistry. So we take the publicly available information, load it in the model, and it projects a weight for that vehicle. So the output of that model I'm showing here is the estimated curb weight against the manufacturer reported curb weight. We're about a 95 R², so we account for 95% of the variation in the fleet. But we do see variation, obviously. And that variation is things we didn't put in the model, things we don't know about. We don't know precisely the material usage on all components of the vehicle. We don't know precisely the option level. So we can start to look at these residuals as a proxy for mass efficiency. So as an example, I don't know what car that is, but our mass model projected that it was 2,000 kilograms. The car itself was 1,800 kilograms. So to us, the unknowns, which are material usage and option, are part of that mass efficiency. So we would say that that's a mass efficient car. If you go on the other end of the spectrum, a car up here, our mass model projected 2,200 kilograms, but the manufacturer said it weighed 2,700 kilograms. So we would say there's something about that car. We've accounted for all the things in that car. We've counted how big it is, the tire size, the engines, it was in a hybrid, the mass of the motor and the battery, and it's still 500 kilograms heavier. So there's a mass efficiency element. So that's what we use the proxy for this study, is the residuals out of the model. The residuals are accounting for everything we know about that car, the unknowns, material use, and option. So there's a distribution around here from mass inefficient to mass efficient vehicles. And we want to look at that distribution. We want to see how that, what that looks like, and study vehicles on either side of that. So this is, if I cut across here, basically look at that distribution, this is what that distribution looks like for the 2014 vehicles. So I have this residual, and this would be percent mass above or below. Don't worry about the numbers so much. Anything to the right here, or right, is going to be less mass efficient, going to the left, more mass efficient. The zero value here really represents what is typical in the fleet today. So what is typical in the fleet today? Leveraging our literature survey, typical in the fleet is, if we start with the body, it's typical as a steel body. We don't know the percentage of high-strength steel, but we know it's typical as steel body. Closures, doors, hoods. There's a fair number of high-volume vehicles with aluminum closures. Fair number of high-volume vehicles with composite lift gates, things like that. So body, steel, closures, some alternative material. Powertrains tend to be almost all aluminum, at least the blocks and the heads of the engines and the transmission cases. Internals of those remain steel in terms of gears and things like that. Suspension components are typically aluminum now. There's a lot of aluminum use. And so that would be the zero. So as you go to the left, we want to look at to calibrate ourselves, we want to look at some vehicles that have done something with mass that we know about. So I picked 3 vehicles here for a reason. The first vehicle is a Toyota Corolla 2014. So it's about 8% below the median. So we would say it's 8%, it's been 8% light-weighted if we want to use that vernacular. Why did we pick that car? That car's a steel-intensive design, but Toyota just went through a redesign on that vehicle, did a lot of activity to take weight out of it. That's where they ended up. The next vehicle over is not in the data set, but we placed it here. It's the 2015 Ford F-150. It's at about 11%. Okay, so it's aluminum intensive body, high-strength steel frame in that case, a pickup truck. It's about 11% below normal. So, and then all the way over at about 19% below is the BMW i3. If you're not familiar with that, that's an electric and a range extended vehicle. It's a carbon fiber intensive body on it. So the progression of lightweighting here from our residuals certainly makes sense, that The BMW i3, by our measure for 2014, is the most mass efficient vehicle. Makes sense, it's also the most carbon fiber intensive vehicle. Ford F-150, lots of activity there, 11%. So remember those numbers, 8% is a redo of a steel vehicle, 11% is an aluminum intensive vehicle, and in a carbon intensive vehicle, at least sample 1 here is out on the end. So going beyond 20% with conventional materials, we would say the probability is quite low. We needed to understand these distributions for different vehicle types to understand the classification and where we're going to set the percentiles. Overall, the vehicle model is neutral to vehicle type, meaning it doesn't bias a pickup truck against an SUV or a sedan. They're all centered around 0 for the most part. So I'm showing here on the left chart all vehicles against just SUVs. You see the distribution is very similar, SUV to all vehicles. On the right, I show pickup trucks to all vehicles. Now, pickup trucks, in this case in 2014, are much narrower distribution. The distribution is centered around 0, but it's narrow. And it's narrower because that's a very homogeneous group of vehicles in 2014. They're all primarily steel, basically what I described earlier. Steel type vehicles, aluminum closures, aluminum powertrain parts. The F-150 is not in here for 2015, but just as a reminder, it moves it down to that 11%. So that's where the F-150 would be against pickup trucks. So again, we felt that the model itself is vehicle type neutral. It's just, again, the pickup trucks are narrower because they are more homogeneous as a group. Option level was something else we were aware of and we can't control, but we did want to look at luxury versus non-luxury. So a luxury vehicle in general, its base is going to be much more heavily optioned than a base vehicle that's in a non-luxury. Certainly you can get a non-luxury vehicle and option it up to have everything, but reporting of masses are typically on base weights. When we broke apart the vehicle data set by luxury, non-luxury, in this case I'm showing sedans because it's the largest set, we saw about a 4.3% separation. This also aligned with where some manufacturers report base mass and fully loaded mass, and it tends to be 3 to 4%. So luxury vehicles, by the definition we used Ward's Automotive to help classify these vehicles, whether they were luxury or not, is about a 4% difference. And we use that across all luxury vehicles, not just sedans. So in the end, we had to select best in class mass efficiency. Neutrality of the model, as I said, we just went with non-luxury and luxury categorization. We looked at the distributions and we recognized variability. Now in the mass world, there's less variability. Weight is more easy to measure. So we're going from tires, which there's no information on, to mass, which there's a lot of information on, at least the weight of the vehicles. So our certainty is getting better. So for that, we picked the 98th percentile for non-luxury vehicles, which is a 10.3% mass reduction. Now, think about what I just said about the Ford F-150 it'd be an 11 on this, so we're saying 10.3. So this is not an insignificant amount of mass, just if you look at it from a program level. For luxury vehicles, we accounted for that 4.3%, and we test them at 90% of the entire group. So still about a 10% reduction, but it's a 10% reduction from a class of vehicles that's starting out at 4% heavier. So to achieve this best-in-class mass efficiency, as we would measure it, as we've assessed it, would be a 10% mass reduction. But again, it's not a 10% mass reduction on every car in the fleet. Some cars are going to get a 20% mass reduction, and others are going to get no mass reduction. So a car out here that's sitting at at 12% residual is going to get a 22% mass reduction when we run the analysis in the end, which we'll talk about. So what were our load scenarios? So now we've gotten, at this point, we've estimated aerodynamic drag, CD, for all 1,300 variants. We've estimated tire rolling resistance for all 1,358 variants. And we have a mass efficiency value for all 1,358 variants. We've defined now the best in class of each of those as 75th percentile for tires, 90th percentile for aero, and 98th percentile for mass, or 90th if it's a luxury vehicle. Now understand that a vehicle could be a luxury vehicle with balanced tires in a sedan class. It could be a luxury vehicle with performance tires in an SUV class. So the vehicle won't be classed the same in every one of these classes. It's going to be classed depending upon what it is. The first thing we did is we ran the baseline. At this point, we're into simulation mode. We ran the baseline scenario, then we took every car and we moved every car to best in class, or if it was already better than best in class, it didn't move. Then the next step is we moved every car to best in class tire rolling resistance. Again, if it was already below best in class, we didn't change the tire rolling resistance. Then we added mass efficiency on top of that. So light-weighted every car that was heavier than best in class, left the weight alone for every car that was better than best in class. Now at that point, the car is going to perform better than it was originally. If I take 500 kilograms out of a car and I leave the engine, it's going to be a lot faster. So what the CARB team asked for is essentially readjusting the powertrain to maintain the performance of the vehicle in its original level. So if the car was 2,500 kilograms and we took out 2,000 kilograms and had a 5-liter engine, we were going to have to take it down something less than 5 liters to maintain that performance. Once we did that, the vehicle now has better fuel economy, so therefore it has better range. So if it's a fueled vehicle, we can shrink the gas tank down, take some weight out to maintain the range of the original vehicle, range being how far you can go on a tank of gas. If it's an electric vehicle, we can shrink the battery down, maintain the range of the electric vehicle. So once you go through all 6 of those simulations, we did about 8,000 simulations in total. First, I want to show you the results of the what happened to the load elements from an averaging standpoint. So the CARB team provided some sales for each of the 1,358 models. So what I'm showing here is the sales weighted and unweighted average of these performance metrics for the entire fleet. So if I look at aerodynamic drag, the average unweighted was 349, the weighted was 333. When we were all done moving everything to best in class, the average went down to 308 for unweighted and 298 for weighted. Now, why the difference between unweighted and weighted? It just says that the high volume cars in general have better better aerodynamic drag than the cars as a whole. We're equally weighting on the blue bars, equally weighting every vehicle. So a vehicle has very poor aerodynamics, but they only sell 100 of them versus a car with good aerodynamics where they sell tens of thousands. So the orange bars here are the more important, but we wanted to show both. So we saw an overall reduction of 10.6% in CD. That's a sales weighted reduction. You remember back earlier I said, depending upon the vehicle, it was 8 to 14% reduction. So it makes sense, we're right in the middle there. For tire rolling resistance is the graph on the right. So we went from a 9 RRC or a weighted, sales weighted 8.2 RRC down to a sales weighted 7.2 RRC. About 11% reduction in overall. Again, In that class, RRC, we were at 11 to 14% reduction. Curb weight went from a sales weight at 1633 kilograms down to 1505, so about 7.8% sales weighted curb weight reduction. The equivalent test weight is what's important here because that is how the cars are tested. Went from 1771 kilograms down to 1642 kilograms, 7.3% reduction if we look at it in an ETW basis. So each car falls into a weight class, and that's how it's tested. The difference between those two numbers is, reason it's 7.8 versus 7.2 is just the baseline number being higher in the case of the test weight class. So that's what, oh, one more. As I said very early in the presentation, tire rolling force is a function of the coefficient plus the weight on the vehicle. So when we take rolling force down and we take the weight down, we're taking the whole force down of the tire. The combination of the lower mass and the lower RRC takes about 18% reduction in tire rolling resistance, or tire rolling force. We look at the total road load force. This is that curve that I showed earlier in presentation. We take it down about 12%. So the non-mass side of this is being reduced by about 12%. So that's what happened to each of the elements when we moved everything to best in class. That's what happened to the sales weighted. So what happened then? What does that mean from a fuel economy and CO2 standpoint? The first thing we want to look at is what happened to the energy. Now I'm going to change names on you because it's the terminology we use is vehicle energy intensity. That is the tractive energy. It's the amount of energy it took to move that vehicle through the cycle. So it's a measure of what's happening when we take out the loads of aero tire and mass and put it into a single number, this total tractive energy divided by the distance. So we went from a 486 down to a 436, which is an 11% reduction in tractive energy. Now, when we downsized the engine, we only changed displacement. We did not change what the engine was, so we did not assume a mass change with that downsizing. So the engine stayed the same, the energy stayed the same. And when we went down, when we took off the onboard energy storage, the change in mass was small enough that the change in energy there is in the fourth digit. It's not, when you take 2 or 3 gallons out of fuel that's 18 pounds, it's not showing up in our analysis as being significant. And for the electric vehicles that may have had a move, there's so few of them in the fleet now that the sales weighted doesn't show up significantly. So that's what happened to energy when we went through the projections, and this is vehicle energy. But let's now talk about fuel consumption and CO2 emissions. The first thing we wanted to do is just check our projections against what was reported and what was projected. So if we took reported fuel economies for every vehicle and reported CO2 for every vehicle, those are the blue bars, unweighted, sales weighted. And let's focus on sales weighted here. So if we took the reported values for every vehicle, we would get 2.964 gallons per 100 miles. Our projections of all those vehicles would be 3.03, so percent or so different. And in the CO2 world, we were ending up with the same projections for the sales weighted. Now we should never, it's by chance that we're matching here, because quite frankly, out of 1,358 vehicles, not every vehicle has a reported unique fuel economy or CO2 value. Because the manufacturer will report a value that's available in the public record, say for a pickup truck, but that reported value may cover a wide range of pickup trucks. We're actually modeling the wide range of pickup trucks, although the blue bar might have only one value for that pickup truck. It's covering all these cabs and beds. But we walked away from this projection to say, yes, we're projecting quite closely what the fleet is coming out at. So let's look at the end results here, but let's look at first at energy conversion efficiency. Earlier in the presentation, I talked about you had the two organizations and they interact. Well, this is the first interaction. Any mechanical device, any energy conversion device, electric motor, an engine, a transmission, if I take the load off of it, it's going to become less efficient because there's this underlying parasitic loss that remains constant. So what happens when you take the load off of a vehicle, this is the total energy conversion of the baseline is 21.9% efficient. That means that 21.9% of the fuel energy that went in actually went to move the vehicle through the cycle. The remaining 78% heated up the world. As we took the load off these vehicles, we dropped down to 21.1% efficiency. This is what we would expect. But it's one reason downsizing trend is going the way it is, because I'm making that engine work harder, and it's going to be more efficient when it does that. By the way, in the downsizing and lightweighting literature, you often see that there's always this claim of a compounding effect, where I can take the mass out of the vehicle and I'm going to get a benefit, and then I can downsize the engine too now because I have less mass, and therefore I'm going to get an additional benefit. The reality is you have to downsize the engine to get the benefit, so it's not a compounding effect, it's just a necessity of rematching the powertrain. So there's a little bit of double dipping that goes on often when you read the literature. But this is what really happens. Now, when we downsize the engine itself, we gain back some of the efficiency. And we were asked, and it's beyond the scope of the study, can you get it all the way back? The short answer is yes, but again, it's beyond the scope of the study. You'd have to get into shift schedules and final drive ratios and things like that to re-optimize that powertrain for that new lighter load. But certainly just downsizing the engine will get you back a significant portion of that. So now I've reduced the tractive load. At least initially I hurt the efficiency, but I got some of it back. So what does that mean from a fuel economy standpoint? Baseline of these vehicles went from 33.3. By the time I re-downsized everything, took out the tractive, we went up to 36.3 miles per gallon. We gained 3 miles per gallon by moving, the fleet gained 3 miles per gallon by moving the entire fleet to best-in-class aero tire and mass. So it's 9.1% benefit. We can get more than that if we could optimize back to the 21.9% efficiency. We'll talk about that later. Now again, just to be clear, some cars might have moved no miles per gallon because they were already best-in-class aero tire and mass. Some cars may have moved 8 or 9 miles per gallon because they were heavy and had poor aerodynamics. But the fleet moved 3 miles per gallon. If we take that and we convert it to CO2, we're moving from 263 grams per mile down to 241 grams per mile, for an overall reduction in CO2 of 8.3%. Now that's 8.3%, dropping the tractive load to best in class and taking the engine displacement down to rematch the performance, but it is not rematching to get back to the original efficiency of 21.9. Again, the reducing the onboard energy storage did not make a significant change because the tractive energy did not significantly change. So a lot of words here. I'll summarize some of this up. Reduction in aerodynamic drag, 3.3% lower vehicle energy, 5 grams per mile, fleet weighted in the California fleet. That's aerodynamic drag. Tire rolling resistance is an additional 2.9%, an additional about 5 grams per mile in the current California fleet. So aero and tire by itself would be a 10-gram benefit, plausibly. Going to best in class of mass efficiency, another 4.8% reduction in CO2. to a total of 17 grams. Then if we resize the powertrain, we get an additional benefit of 5 grams. So now we're at 22 grams per mile. So that's taking everything to best-in-class aero, tire, mass, downsizing the powertrain to at least maintain performance. Now, as we said before, to recover the full efficiency, get from the 21.5% back up to the 21.9, 22% efficiency, there would have to be more done to the powertrain from an optimization standpoint, mainly in control and some hardware. If we could take it up to 22% back to the baseline efficiency, so we're not taking the efficiency beyond where it was, we're bringing the efficiency back up to where it was, we would get another 5 grams out for a total of 27 grams per mile. So concluding all of this is bringing everything to best in class could reduce the overall vehicle load by 10%. That's again re-optimizing or adding plausible levels of aerodynamic drag, tire rolling resistance, and mass efficiency, resizing and re-optimizing the powertrain. That would yield anywhere between 8.3 if we did not fully re-optimize the powertrain to 10.4 fully optimizing the powertrain. The majority of this potential is the direct result of vehicle load, 64 to 80%. Optimization and resizing of the powertrain is the remainder. What does this mean overall? 10% represents about 1/3 of the total reduction that is being sought in the California Advanced Clean Cars program. And with that, I can take questions.
Oh, you want to give it to him? Oh, yeah.
Go ahead. Okay, this question comes from John German at ICCT. The B coefficient does not have any physics-based relationship to tire rolling resistance or CD. Further, the B coefficient varies widely from vehicle to vehicle, from small or even negative values to very large values. How did Controltec decompose the B coefficient into tire rolling resistance and CD?
Okay. So the short answer is from a physical standpoint, the B coefficient represents the change in force with speed. The C coefficient represents the change in force with speed squared. So tire rolling resistance, its most important is the A coefficient static, but it also has a very strong speed coefficient to it. And this is well recognized. So the B coefficient is actually a relationship in tire rolling resistance. Relative to the details of decomposing, I would refer to the report on that. I'm not sure when the report will actually get published here in the next month or so, 2 weeks. But we go through how we do it. We're really looking at the derivative of the curve, and we're taking out some additional losses for tires, but we describe it in detail in the report. We also compare it against the typically in the industry, there's a lot of papers that will go through and say if you use the C coefficient alone and use that to estimate aerodynamic drag or CDA, you get an answer. We show that in the paper. We actually compare our derivative model against the C coefficient alone, and you see in the paper there's much higher agreement with our derivative model.
Okay, another question from the internet, this one from Stephen Zoff at DOT. There's 2 questions. The first one is, did Controltec attempt to control for downforce in the performance vehicles? They mentioned that coupes have higher CD than sedans, possibly due to downforce inducing elements that cause higher drag. So if we move all vehicles to best in class or 90th percentile, are we inherently assuming some trade-off in downforce? Answer that one.
Did you want to go to the second one or just read the first one first?
One at a time.
All right, so it's a good question regarding CD and downforce. We did recognize that. We did look at other performance vehicles in that sector to see, is it only, is it common to every performance vehicle? And the short answer was no. Now, we did not try to attempt to offset that in any way. We recognize that there's a passive downforce that those manufacturers will want. Perhaps you can do it with an active device that's deployable at speed or some other methodology. We did not go into that side of it. But there are performance cars in the data set that have good coefficient of drag.
Okay, and his second question, improved aero would directionally lead to better energy capture from regen in electrified powertrains, as less kinetic energy is scrubbed off through aero. Has CONTROLTEC attempted to capture or quantify this difference across vehicles with regen, for example, hybrids, EVs, plug-in hybrids, and without?
Yeah, the short answer to that, good question. So, tire rolling resistance and aerodynamic drag are essentially a negative to any vehicle trying to capture kinetic energy. We do recognize that. The simulation model that we use accounts for that. So we compute the kinetic energy available across the cycle. So as we reduced aerodynamic drag and tire rolling resistance, there was more kinetic energy available for the hybrid vehicles. So it did account for that in the simulation portion.
Okay. Alberto.
Thank you. Alberto Ayala with the California Resources Board. My question is a little different. Can you help me understand, how should I be thinking about the results, meaningful results that you obtain based on model year 2014? Obviously, we're trying to understand what this is telling us in terms of trends, and just based on your previous experience, should I be thinking about these results as indicative of reasonable potential for the future, and they are consistent with what you've seen with similar analyses in the past?
Yes, it's a good question. We see it as what could be reasonably expected to pull out in terms of tractive force if we're planning for the future. And that's really whether you're an OEM planning for the future or a tire or somebody else planning on the future. What has other companies done? And if everybody could do those things, what is the potential? So we see it as a plausible level of reduction. I mean, you can balance that against other studies that maybe take radical reductions. Then you get into the whole discussion of, well, is that radical reduction really achievable from other elements, costs and safety and everything else? This study, I think, just puts a boundary and says, here's a plausible level that we believe that over 1 or 2 generations of vehicles the fleet could get to. Whether they're going to do it or not is another question, but it's certainly plausible. And if we go to the mass side, for instance, we'd say, okay, I use the Ford F-150. I think everybody that's following the vehicles in the fleet, we would say that's an aggressive lightweighting program. They spent a lot of money on that program. That's where they're at. And could everybody get to that level? Perhaps in a couple of generations of car, generation of car being, say, a 6-year cycle. So certainly, if they did it, it's plausible. We didn't talk about costs or anything else, but plausibility. So that's how I would view this, is plausibility.
And my name is Seungju from California Air Resources. I have a question about your simulation tool. I believe it is simulation tool account for physical power requirement by different component. But that model, I'm not sure if you account wind direction and wind speed, because in California, we have always a very high wind and all year round. So if you account the wind direction and wind speed to your model, given that the best in class coefficient, the fuel economy you estimated up to 10.6%, will that percent significantly change?
Okay, so it's really a good question, really reflecting real world, I think is what you're getting into. And we did not study real world here. So this would be, you can view these results as really the certification level. What could a manufacturer get to from a certification level, which is on a dynamometer in a controlled environment running on the EPA cycle. I could not answer with any kind of accuracy what would happen with wind. Certainly if it's coming at the car, it's going to be worse. And then drive cycle is very important because does the California fleet drive like the EPA cycle? So that's a whole other question. So I think your question, I take it, I can't answer it directly. They're all valid points, but it's really about real world, what's going to happen in real world. And if there's a lot of wind in a certain area, then certainly aerodynamics is going to up its importance, especially if you're getting a lot of wind in the direction of movement or against the direction of movement.
We have time for a few more, so feel free.
As with any good research, you answer one question and typically generate two more. Based on your experience with this work, what would you advise the Air Resources Board do as a follow-up in terms of recognizing that our goal is clear. We're trying to reduce greenhouse gas emissions from our cars and trucks. Based on what you learn here, what would you say would be good additional questions to pursue in the next study?
Very good point. It's a difficult question to answer. So first is, this is a single model year, single data point. So one thing that looking forward is to say, well, what is the trend of the industry? Maybe 2 years out, do the same thing to understand where the industry is moving. As we went through this, we certainly wished we had data from 10 years ago at this level of detail. So we need another data point initially to understand where things are moving and reset some of these analyses. The 0 point in mass is going to be different in 2020 than the 0 point in 2014. And how is it moving? Same with aero and tire. So trend-wise would be one, but how to use it and where to go from here, certainly, again, it sets that level of plausibility. Do we think we can do 30%? We would say, based on what we're seeing, that in the next 2 generations of vehicles, 6 years, it'd be very, very difficult and highly, highly unlikely because of everything that has to do. So this allows you to set that goal. But that would be number one item. I think there's more detail that we could get into, more scenarios to look at with the information. We stuck with the EPA cycle. For the other gentleman's note, what about the World Harmonized Cycle? What about, we understand California collaborates with other agencies across the world. What does this mean for the NEDC? What does it mean for other? And then when you get into, say, more electrified or vehicle mixes, you can start to run models. The same data set, but different mixes. The absolute levels, this 20 to 27 grams is based on the current mix, which is highly SI a very low volume of hybrids. Now, if I applied these same results to a highly electrified fleet, those numbers are going to be very different. And we will leave their resources team with that information so they can manipulate different scenarios and see what would happen. Say you go to a 25% electrified fleet versus about 5% now, I think, is where you're at. So scenario generation could be the other. I think looking at perhaps heavy-duty truck in this area could be helpful. Might be more difficult because the amount of information available might not be there the way it is for light-duty vehicles.
We have a question coming in from the internet, so hold on for a minute. It's going to be hot off the presses. Okay, this question is from Chris Nevers at Auto Alliance. Greg, if the vehicle mass was described in terms of equivalent test weight instead of curb, would it change the mass efficiency portion of this study?
Okay, good question, because let's just go back. You know, these results here are based on curb weight, and just to kind of refresh, when a car gets tested for certification, you add 300 pounds to it to get the loaded weight, and then where you fall within a range of weights is how the vehicle is tested. So a car could end up at some value and get tested at 3,750 or 3,875 pounds or 4,000. So there's discrete incrementations. The short answer to Chris's question is it would not change the aggregated results or the fleet level results. But it would certainly change individual vehicle results. So when I bring up this slide here of curb weight versus, yes, sorry, slide 43. So in slide 43, the curb weight, sales weighted, is going from 1633 to 1505. Quick math there, what, 128? And then we go over to the ETW, and it's moving about the same. I think it's within a kilogram or two. So on average, the ETW is tracking the curb weight, but there will be vehicles individually that are going to move more or move less. The overall aggregated value should be the same.
I guess we have time for one more question. Apparently our clock is not accurate.
Hi, this is Kevin at the California Resources Board. I was wondering how amenable are your analyses for doing different drive cycles that might reflect more real-world acceleration, maybe more aggressive acceleration, more idling, more traffic?
Yeah, good question, because it does change the results for sure. And the simulation model that we use, as long as we have the drive cycle from a 1 second interval, it actually doesn't have to be 1 second, whatever time trace you have. If you have grade on your drive cycle, it takes in grade as well. So what we actually ran, but we don't show it in the report, is all the cycles. So all the regulated cycles. So we did run the US06 and the SC03, we did run the NEDC, we did run the JC08, which is used in Japan, and we did run the World Harmonized Cycle, all four. But if California had a California driver cycle, we could certainly load it in and run the California driver cycle. We have an interpretation, if you're familiar with Consumer Reports, we have an interpretation. We don't know their cycle exactly because they don't publish it, but we have an interpretation of it, and we run that as well. And our results correlate pretty well to their results. Does California have a California driver? Okay.
Okay, well, now we are out of time, so I'd like to thank Greg for a very informative and interesting way to look at the fleet.
All right,
Awesome.
thank you.
And that, I guess, concludes our presentation. Thank you.
Appreciate it.